Hello, everybody. This is a presentation for the International Conference on Software and Systems Reuse. I am Nicolas Anquetil, and I am going to present our paper, Modular Moose, a new generation software reverse engineering environment. First, the agenda of the talk. So I will discuss a bit reverse engineering requirements. And then we will see that we need metamodels, generic software metamodels for this. And I will present our metamodel, which is called Famix. But Famix had issues that we solved in the new generation of Famix that I present after that. And I will also present Moose, an integrated reverse engineering environment, which is based on FamixNG, before I conclude the talk. So this is first reverse engineering requirements. Reverse engineering requires many different tasks. It involves many different tasks like navigation, visualization, querying the model of the software, analysis of data or control flow, etc. And also you have to work with huge data. When you have systems of millions of lines of code, you also have millions of entities to deal with, classes, methods, variable, accesses to this variable. And finally, the different tasks involved require specialized tools that are costly to develop. So the question is, how can we reuse such tools so as not to redevelop them all the time for each new system or each new language? We want to reuse them across system, programming language, across organization, different way to work. And this is typically done by using metamodels to model the programs that are to be analyzed. At AirMod, we have a platform for software analysis that is called Moose. This platform is based on a generic metamodel that we call Famix, and I will present it shortly after. The platform is developed since 1996, and I give you here two pointers for more information on Moose itself and the source code. So Moose is a platform software for software analysis. It's based around a metamodel which we call Famix, a metamodel of software programming languages. There are several importers that can import data from different languages into the model. Then there are tools and visualization that can use these models to help people doing reverse engineering. So here is some example of the importers that we have. We can import source code in many different programming languages. Not all of them are complete, but you can see that it ranges from procedural to object-oriented language. It includes SQL and things like that. We can also import HTML, XML, CSV, things that are not purely programming language. And finally, we also have importers for bugs and commits and authors. The tools that can work on a Famix model, one of these tools is Moose Query, which is a DSL to query and navigate a model to find entities from an entity to find all its dependencies, for example. We have computation of various software engineering metrics, cohesion, coupling, cyclomatic complexity, the metrics bias, Dambler, and K-error. And we also recently added some data mining algorithm. And these are examples of visualization. These visualizations are built on a tool that is called ROASAL, and that allows to construct these things quite easily with some scripts. I will now present the generic metamodel Famix that we are using, and that is the base of Moose, the core of Moose. So what is a generic software metamodel? Basically, intuitively, one could think it's easy, We want to be able to represent packages. Packages contain classes that can inherit from other classes. Classes also contain methods and attributes. Methods can invoke other methods. Method can access attributes. And with such a simple model, one could think that we can represent many object-oriented languages. However, things are a bit more complex in real life. And here I'm showing a small part of the real Famix Metamodel. And you already see that there are many more entities involved. For example, we have sourced entities that can be comments or association or variables, etc. The association, you have inheritance, you have invocation. So an invocation is between a method that can invoke another method, and there is a receiver. You have the named entities, entities that have a name. This includes leaf entities, which are basically variables, parameters, attributes, container entities that can be types, for example, packages here, or behavioral entities, functions, and methods. And the problem of Famix is that it suffers from the tyranny of the dominant decomposition. Being based on single inheritance, you have to decide how you will choose when there are several possible inheritance to represent. And we can see one of the problems here is that a method can invoke another method. And when you invoke a method, there is a receiver, which can be a class if it's a static method, or it can be a variable, an instance if it's a non-static method. So the receiver of the invocation, as one can see, has to be a named entity because variables are here and types are here. And this is not very satisfying to say that the receiver and invocation is just a name entity because a package is also a name entity, and this doesn't make much sense. We are not the only one to have this problem. For example, here I give another example with the Dash tool middle metamodel, and you can see that they represent model element and model relationship, and this means, for example, that a field could include a type, or a field could invoke a routine, and this kind of relation that are not natural. So yeah, the conclusion is that having a generic software metamodel is not easy because quickly you can have entities that have unneeded or misleading properties, and such Famix, for example, because of this was difficult to evolve to add a new language because you have to understand the whole model, which is quite big, and the fact that you want to add a new language sometimes could cause a property to go higher in the inheritance hierarchy, and so it would change all the models as a consequence. To solve this problem, we decided that we wanted a composable software metamodel and that we call FamixNG. So the idea is that instead of having one generic metamodel for all languages, we want to be able to create specialized metamodel for each new language. FamixNG is composed of a set of what we could call bare-bone entities, very simple entities like in the example here, a class have attributes and methods and inheritance, and that's only this. And on these bare-bone entities, we could add composable properties. For example, here, a property would be that a class can also have visibility in Java. In C#, a class, you have the definition of partial classes. In Faro, classes can have extension or they can use traits. So from the bare-bone entity class and with different composable properties, we can create a specific entity for a specific language. And this is what FamixNG tries to do. FamixNG is basically a composition of 100 traits. Is a library of 100 traits. And what is a trait is we can think of it as a small class, a set of methods that can be added to real classes. We say that a class uses a trait, and the advantage is that a class can use multiple traits. There is still single inheritance between classes, but with traits you can use multiple traits. Here I'm presenting two examples of traits. So, for example, we have a trait that is t-named entity, and this trait will be used by all entities that have a name. The traits only define this, that an entity has a name, and that's it. We have also another trait called t-namespace, and this trait just defines that an entity contains named entities, and a namespace is itself named. From these two, we could, for example, define Java packages and Java classes. That way, a Java class is a name entity, a package uses t-namespace, and at the same time uses named entity. And so a Java package can contain a Java class. Similarly, a Java class uses t-namespace, a Java method uses t-named entity, so a Java class can contain Java methods. This is the definition of the generic t-class entity in traits. This is the definition of the generic t-class trait in FamixNG. It uses t-types, so a class is a type, which means that it is a named entity because a type uses named entity. A t-class can have comments, it is packageable, it has inheritance, attributes, methods, and it can be an invocation receiver. From this t-class, we can define specific Java class, Faro classes for different languages. So the Java class is a t-class. It has all the properties that I presented just before, but it also has a visibility and it can use exceptions. A Faro class doesn't have visibility, but it can use traits and it has extensions, which is a specific Faro feature. So here I give an idea of the FamixNG library. The more than 100 traits are decomposed in four categories. First, the relationship traits, like a trait that says that an entity can have inheritance, it can access variables, it can invoke a method, it can make reference to another type, it can use trait, meaning it can kind of inherit from a trait, and it can include file. This one is more specifically for C programs. Then there are technical traits, 12 of them, that are used to represent the source code of an entity, or to represent, to compute metrics, software engineering metrics, or to compute queries of the Moose query tool that I presented before. There are 46 property traits, which are traits that had one property, like the t-named entity traits that I showed before. So you have this trait here that says that an entity has a name. There is also a trait that says that an entity can have comments, that an entity can be typed, that it has a visibility, that it is invocable, and so on. And finally, there are the entity traits that introduce what I called the bare bones entities, like class, method, exception, function, files, maybe for C. Apart from the traits, FamixNG also use a builder, several builders, different builders for each language. So when we want to create a new language metamodel for a new programming language, we use a builder. The builder uses a small DSL to describe the language, the entities that we will allow to have in their language. And this DSL was inspired by plantuml.com. So quickly, this is a script in plantuml.com. And if you give it this script, it will generate you this UML diagram. We don't care about the UML diagram, but we reused the syntax of plant UML in our builder. So this is an example. Here we will do a simple metamodel to represent commits, and the metamodel is here. First, we define the classes of our metamodel. So we say that we have entities, we have files, we have commits, and we have authors. And in blue, you see the DSL that I was describing, the DSL of the builder. After that, we can define properties. So we say that a commit, for example, has a property named revision, which is a number, it has a date, it has a message. After the properties, we define the inheritance. So a file is an entity, but a file also uses the trait t-named entity, which means that a file will have a name. A commit is an entity, an author is an entity, and an author also uses the trait t-named entity, so authors will also have a name property. Finally, we define the relationship, and we say that files are related to commits, and that every commit has an author. So this is it for this short presentation of FamixNG. And now I will show Modular, our new integrated reverse engineering environment. So to come back to what we said at the beginning, reverse engineering involves many tasks like validation, query metrics, etc. These tasks require specialized tools. We want these tools to be generic across different metamodel, different programming language, and we want also them to be adaptable and to be able to collaborate. For this, we have Modular, which architecture is described here. So Modular is based on different tools that communicate through information buses here. A tool can be attached to one information bus or to several. These tools actually, they are graphical tools that use the infrastructure tools that we already saw, for example, the DSL to query models or the scripts to create new visualization. And these infrastructure tools, they use data from the different language metamodel that we have, and the language metamodel are built from the FamixNG composable traits. The rules in Modular are the following. The environment, Modular, centralizes all data and tool interaction through the buses. Each tool is focusing on a single task. For example, we have a query browser that I will show just after, that works on a set of model entity and through a query produce another set of entity. And tools communicate through buses. They read model entities on the buses, work on them, produce something, and write the entities back on their buses for other tools to consume them. So this is an example of the query browser. You see here that it's attached to a default bus. From this bus, it read an entity which is a model, and we create a query that says I want all the classes in the model. The result was 25 classes. These classes were written on the bus, and some other tool that that is also on this bus will see the classes and deal with them. In this second step, we added a new query. We refined the query by saying we also want it to be abstract, so that we want the classes that are abstract. And now the result is only 4 classes that again were written on the bus to be consumed by some other tool. This is an example of another tool, which is the Dependency Graph Browser. What it does is it reads entities incoming in the bus, display them, and display their dependencies between these entities. So here we can imagine that all these entities were produced by the query browser tool. This is yet another tool that reads a certain entity, and from the certain entity, you can see the properties of this entity. Communication buses. So as I said, tools can read and write model entities on the buses. Each tool can be attached to 0 or 1 buses. When a tool is attached to no bus, the display doesn't change, and this can serve as a reference to compare a initial result with some other result later. We can also have several instances of the same tool on different buses. And for example, you can imagine a bus number 1 with a query browser and a dependency graph browser, and a bus number 2 with another query browser and another dependency graph browser. The first query browser will create a query, produce some entity that will be consumed on the bus by the dependency graph browser, showing the dependencies between these entities. Here in the query browser 2, we can produce another set of entities on the bus 2, and the dependency graph browser 2 will present another set of dependencies, and thus we can compare the dependencies between two different sets of entities. There is also a finer way of controlling the behavior of the tools with 3 modes that the tools can have. The follow one is the default one, where the entity read entity on the bus, deal with them, and then produce entities on the bus. In the frozen mode, the tool doesn't read incoming entities in the bus. It just keeps the same display that it already has. And this, as I said, is a way to compare a result for one set of entity to another set of entities. This is a bit different as not being linked to any bus, because the tool can still produce new entity. If you click here, for example, on this entity, it will be produced on the bus and other tools can use it. Finally, there is the highlight mode, where the display is frozen, but when a new entity comes on the bus and is read by the tool, it will try to find this new entity within its display and to highlight it. So this is a way to highlight a new result in the context of a result that was obtained previously. So now I reached the conclusion. I presented FamixNG, our new compositional programming language metamodel that works with a library of basic traits. I also presented Modular Moose, an interactive reverse engineering environment with a specialized tool that communicate through buses. Thank you very much, and I hope we will meet at ICSR 2020.